This is an example of the conservation of mass for differential control volumes. We're going to start nice and simple for you here. Remember that the conservation of mass for a differential control volume looks like this, where we have a transient term and 3 convective terms. And what we want to do is just start with a very simple problem. The example that we're going to do is that it is a steady, incompressible, two-dimensional flow. And so what we want to start with is we always start with the most general form of the equations, and we want to simplify it as best we can before we even get started. So if it's steady, we get to get rid of the time derivative term here, steady. And so that goes away. If it's incompressible, what that means is that we can pull these densities out, and because this term's gone, we can divide that out and there's nothing on the other side, and so all of the densities are gone because it is incompressible. And then lastly, it's 2D, so let's just drop this one. We'll drop the z direction, we'll use the other 2 coordinate directions. And so for steady incompressible 2D flow, we're left with a simpler version of the conservation of mass that looks like this. And what that tells us is that du by dx has to be equal to negative dv by dy. And you might be thinking, yeah, and? Well, this works in a lot of places, but one place that you might use it could be a pipe T. So we have some intersection that looks like this. And you could imagine that we have a velocity going in here, which would be u1, and a velocity here, which would be u2. Maybe going in this way is a thing that looks like v1, and a thing that looks like this, looking like v2. What this is saying, this du dx is equal to negative dv dy, is that if there's a change in u, that change has to be reflected equal and opposite in v. In other words, what this can be interpreted to be saying is that u2 minus u1 has to be equal to negative v2 minus v1. And so if you knew some of them, you could find the others, and so on and so forth. The idea is something comes in here. Let's just pretend v1's 0 for a minute. Okay, here, hang on. Let me get a little bit more to work with. Let's pretend that v1's 0, that this is actually a solid wall. Now this might make sense. If I've got a whole bunch of fluid coming in at this location 1, and some of it comes out here, all this is really saying is that the delta between those has to be captured here. In other words, however much goes in here, some comes out there, all the rest of it has to come out there. That's how you can interpret this. Now we can make that slightly more complicated by actually letting v1 have a value too. And so v1's coming in, u1's coming in, some amount of that goes to the right here at u2, and the rest of it comes out at v2.